This is Chapter 4, Linear Models and Matrix Algebra, Part 1. So Chapter 4 and Chapter 5 talk about the matrix algebra, and I'll spend a lot of time talking about them. So last time we talked about the supply and demand functions and also solve for the quantity and the price using simple linear equation. So in this chapter, we'll talk about more complicated problems. So first I'll tell you what is matrices and what is vectors. So suppose we have two commodities that are related to each other. So this is the equations, you should be familiar. This is QD1 minus QS1 equals to 0. So this is the same as last time. But we have two commodities here. So we have D1 as 1, the notation for the first commodity. And then the D2 and S2 is the notation for the second commodity. So here we have a total of 6 equations. So in the first 3 equations, it describes the first commodity. So QD1 equals to A0 plus A1, P1 plus A2, P2. So that's the difference from last time, because last time we only talked about the relation between Q and P. But here, we have another variable called P2 here. Well, that means that the quantity of the first commodity is not only related to the price itself, that's P1, but also is related to the price of the other commodity. So they are related to each other. So the quantity demand of the first commodity is also related to the price of the second commodity. So you can think of that. Think of an example of a table and chair. So the price of the table and the price of a chair may be related to each other, right? So if you increase the price of a chair, for example, you may also increase or decrease the quantity demand of the table. So that's why the price of the two commodities are related to the quantity of the first commodity. And also, the supply quantity of the first commodity is also related to both the prices, right? P1 and P2. So last time we only talked about this situation here, right? We don't involve the second commodity. But here, the problem becomes more complicated because it is a whole system. The two commodities are interrelated to each other. So this is the first commodity, the supply and demand and equilibrium condition for the first commodity. And for the second commodity, everything is similar to the first one. We have the quantity demand of the second commodity equals to the supply quantity of the second commodity. And the demand is related to not only P1 but also P2. Right, and the supply also related to the first commodity and second commodity, the prices. So together we have 6 equations, and we call this a huge system that we need to solve. Right. And so here we can rearrange these equations, the 6 equations, and get these 2 equations here. So we get this first equation by subtracting the QS1 here from QD1. So that is QD1 minus QS1 equals to, so we subtract the second equation from the first equation. So that is A0 minus B0, right, as the first term, plus the second term is A1 P1 minus B1 P1. And the second term is, the third term is A2 P2 minus B2 P2, right? And then we get this. first equation here. And because QD1 and QS1 are equal to each other, so this is 0, right? And also by subtracting QS2 from QD2 and using this equilibrium equation, we can also get the second equation here. So so from the 6 original equations, we can downgrade it to the 2 equations here, the system. And that will be much easier for us to solve, because we now get rid of the QD1, QD2, and QS1, QS2, and only P1 and P2 left in the system. And then we let lambda I equals to AI minus BI, eta I equals to CI minus DI. So that is to say lambda 0 equals to A0 minus B0, and lambda 1 equals to A1 minus B1, and so on, I equals to 0, 1, and 2. So with this notation, lambda and eta, we can change the equation to another notation here. Lambda 1 P1 plus lambda 2 P2 equals to negative lambda 0, right? Because this is lambda 0, lambda 1, this is lambda 2. We move the lambda 0 to the right-hand side. So there's a minus sign here. And also equal to the, also for the second equation, we do the same. So this is eta 0, eta 1, eta 2. Okay. So now we change the 6 original equations into just the 2 smaller equations here. So we call this a system of 2 linear equations. So in these 2 equations, we have 2 unknown variables to solve. So our goal is to solve what is exactly P1 and P2, right? Because all the other parameters, lambda 1, lambda 2, eta 1, eta 2, and this lambda 0, eta 0 are all constants. These are some number that we already know, but we don't know what is P1 and P2. So this is the variables that we need to solve. And this is just the 2 linear equations in this example. But generally, what if we have a lot of commodities, and so we have so many linear equations, right? So generally, a system of m linear equations in n variables can be written as this thing. So here in this little example, we have only 2 linear equations and 2 variables, right? Because this is the first equation, the second equation, and we only have P1 and P2 as unknown variables. So we have 2 linear equations and 2 unknown variables that needs to be solved in this example here. But generally, what if we have m linear equations and n variables here? So we can write the whole system as this. So here, all the a's here, a11, a1n, and all the a parameters or constants. So it's some number we already know, right? Just a constant. And all the x here are the variables we need to solve, or unknown variables that we need to find out the answer of them. And the D1, D2 to Dn, they are also constant terms, right? So this is a generalization of these 2 equations here. Okay. So for this equation system, first we have n equations, right? So this is the first equation, the second equation. So this is n equation. And we have m variables. So they are x1, x2 to xn, right? So these are the variables that we don't know and we want to solve them. Okay, so it's hard to solve this entire system by just looking at it or by hand, right? So what we're gonna do to this whole system is to convert that into matrix algebra, and that will make things very much easier, right? So to change that into matrix form, we first need the three things, right? This is called matrix A, big A. It is called coefficient matrix. So in this big A, the matrix, we plug in all the constant coefficients in this system, right? So that's A11, A12 to A1n, so that's the first row. And for the second equation, we have also n parameters or n constants. So that's A21, A22, and A2n. And for the last equation, the nth equation, we also have m parameters. That's am1, am2, and amm, right? A lot of things in the middle. So we have combined all the coefficients in those equation systems into one large matrix form. So this is called matrix A, the coefficient matrix. And we separate each coefficient by just a space. And there's no comma in between, but just a space. It's like the arrays of coefficients in this form. So this is called matrix. And for the X matrix, the big X matrix, we just combine all the variables we need to solve. So that's from x1, x2 to xn. It's like the vector or a list of the variables. And for the matrix D, we combine all the constant terms on the right-hand side. So D1, D2 until Dn, right? Those are the constant terms in the equation. So now we can transfer this whole generalized equation system into three matrices. So that's coefficient matrix A, the variables, the unknown variables we need to solve, that's X, and the constant terms D. And there's a note, the Aij is the element of the A matrix, right? So all the little a here, or all the X here are called element of a matrix. And the Aij, pay attention to the notation here. For example, this A21. A is called A21 because it lies on the second row and the first column. So this is the notation of the row, the number of row, and so this is the number of column. So for example, A2n, that means that it lies in the second row and it's the nth column, right? So the first column, second column, this is the nth column. So this is an A2n. And AM1 means it's in the nth row and first column. So this is a notation of the different elements in the coefficient matrix. Okay, so here's a little bit exercise. If we look back to our first example here, we can also transfer these two equations into a matrix form, right? But this is a much smaller matrix than this one here. So if we transfer this matrix, it should be So A, let me write down here. This little a should be lambda 1, lambda 2, eta 1, and eta 2, right? We only have 2 rows and 2 columns because we only have 4 parameters here in this example. And for the x, or the unknown variables, we have 2, right? P1 and P2, right? So these are the variables that we don't know. And for the D matrix, it should be minus lambda 0 and then minus eta 0, right? Because this is something on the right-hand side, the constant term. So if we transform this into matrix form, we also have 3 matrices here, A, X, and D. And this large matrix here is a generalization way of writing the things. Okay, so we have our definition for matrix. A matrix is a rectangular array. A matrix is a rectangular array of numbers, parameters, or variables. Right. So here, for the coefficient matrix A, it contains all the coefficients. Here, this is a coefficient matrix. And so this is a matrix of the variables. And this is the matrix of the constant terms. Right? It can be a rectangular array of all kinds of like numbers, parameters, or unknown variables. Right? All of them are called matrix. So for another example, consider we have a linear equation system. So I give you the specific numbers here, not lambda, eta, or a, right? Because this is example here. So we can know that all the parameters here becomes a real number. And the d here also constant number. So we can change the 3 linear equation system into a matrix form. So A here, also the coefficient matrix. So the coefficients here are 5, 4, minus 2. So that's the first equation, right? The first equation. And then it's 2, 3, minus 1. So that's the second equation. And for the last equation, we have 3 parameters or 3 coefficients. They are 4, minus 6, and 3. So together, this is called the coefficient matrix. We have 3 rows, and 3 columns, right? And for the variable matrix, this is X, right? There are 3 unknown variables, X1, X2, and X3. And for the constant term, we also have on the right-hand side 20, 15, and 24 as the constants. So together we can change the linear equation system using the matrix form. And as I said, our goal here is to solve x1, x2, and x3. But it's hard, or it's not easy to find out the answer by just solving the equation from the original 3 equations here. Right? It's not easy to solve using the 3 equations. But if we transfer the system into a matrix form, it will be much easier for us to solve for x1, x2, and x3. But if you really want to solve the whole system, you need to know the matrix operations, right? So later on, we'll talk about how to actually do calculations using matrix. Okay, so here are some of the definitions. If matrix A has n rows and n columns, then it is said to be dimension m by n. So for example, here, this A matrix has 3 rows, right? So there are 3 rows here and 3 columns, 1, 2, 3. So this matrix is called to be dimension 3 by 3. 3 by 3 matrix. And if m equals to n, then the A is called a square matrix. So in this example, n is just n, right? They have the same rows, same number of rows and columns. So the matrix A here is called a square matrix. Okay, so if n equals to 1, for example, x and d here have only one column, right? N equals to 1, so they have only one column, but multiple rows. So if the matrix look like this, then this kind of matrices are called column vectors because there's only one column here, so they're called column vectors. And if n equals to 1, so for example, this matrix, we have only one row, right? But several columns. So if the matrix looks like this, then we call this a row vector because we only have one row here and multiple columns. So this is called row vector. Okay, so after we know the A, X, and D, we can rewrite the entire equation system as A times X equals to D. Right, A times X equals to D. So we haven't talked about the matrix multiplication here, but we'll talk about that later on. So far, we just need to know it's called A times X equal to D. So for example, here we have this A, this X, and a D. So we can change this system into just a very simple way, AX equals to D, right? And if you want to know how to find out the x, you need to know first multiplication and how to find out the inverse matrix of A. But we'll talk about it later on. Okay. So second, let's talk about how to actually do operations on matrix. So first definition is called matrix equality. Right. So matrix A and B are equal to each other if and only if they have the same dimension and identical elements in the corresponding locations in the array. So that means that first they have to have the same shape, right? Both of them should be m by n matrix and exactly the same, and they have the same numbers on the corresponding locations. So for example, so this matrix 1, 2, 3, 4 equals to 1, 2, 3, 4. Right? These two matrices are equal to each other because first, all of them or both of them are 2 by 2 matrix. They have the same dimension, right? They have 2 rows and 2 columns. Pay attention that m by n means this is the number of rows, this is the number of columns, right? The first one is a row, second one is a column. So here 2 by 2 means that we have 2 rows and 2 columns, right? It's a square matrix. So both of them have the same dimensions. And also, for the first row and first column, this element is 1. And also for this matrix, in the first row and the first column, this number is also 1. Right? So number 1 lies in the same location in the two matrices. And for the number 2 here, it's in the first row and second column. And here is also in the first row and the second column. So 2 have the same location, right, in the two matrices. And also the same case for 3 and 4 here, right? So we can say that all the numbers lies in the same location in the two matrices, and also they have the same dimension. So only in this way we can say that the two matrices are equal to each other. And for the second example here, 1, 2, 3, 4 doesn't equal to 2, 1, 3, 4, right? Because you change the location of 2 and 1 here, right? So they are not the same to each other. Although they have the same dimension, but the numbers don't have the same location, so they are also not equal to each other. And also, the third one, you change the location of the first row and second row, right? So this is 1, 2, 3, 4, but here's 3, 4, 1, 2. Right? So you change the location of the rows, so they are not equal to each other. Only in the first case, the two matrices are equal. But if you change a little bit of numbers, so they are not the different matrices. They are called different matrices. So this is a definition of matrix equality. Okay. And after this, we first talk about the addition and subtraction of matrices, the easiest part, right? But before that, we have a requirement. For the two matrices to be added or subtracted from each other, the two matrices have to have the same dimension, right? That's kind of like a prerequisite for the two matrices in order for them to be added or subtracted. If they have different dimensions, for example, 1, 2, 3, 4, 1, 2, 3, 4 plus 1, 2, 3, 4, 5, 6. Right. So this is 2 by 2 matrix. So this is 2 by 3, right? We have 2 rows and 3 columns. So these two matrices, they have different dimension. So they cannot be added or subtracted, right? Only the same dimension matrices can be added or subtracted. So first addition, for example, 2, 4, 3, 7 plus 1, 5, 8, 9. So these two matrices, they have the same dimension, right? Both of them are 2 by 2 square matrix. And if we add them together, we add each pair of elements in the corresponding location. So for example, the 2 and 1 here, both of them lies in the first row and first column, where they have the same location inside the two matrices, first row and first column. So we only add the elements that lies on the same location in the two matrices together. So here, after doing the addition, for the resulting matrix, for the first row and the first column element, the addition result is 2 plus 1, right? 2 plus 1. And for the first row and second column, the element is 4. And again, first row and second column, the element is 5. So for the resulting matrix, the first row and second column, after addition, it should be 4 plus 5. So we only add the elements that have the same location together. And the resulting matrix is also 2 by 2, right? We don't change the dimension of the resulting matrix. It should have the same dimension as the two matrices here, right? And again, for the second row and first column, the result should be 3 plus 8. this element here should be 3 plus 8. And for the last one, the second row and the second column, the result should be 7 plus 9. And then we do a simple calculation, find this is 3, this is 9, this is 11, and 16. So this matrix is the addition of the two matrices here. Right, so this is the result of the addition of the two matrices. So in general, if we have an n by n matrix, we have to add another matrix that is also m by m dimension, right? Because only the same dimension matrices can be added together. So we call this A matrix and this B matrix, right? And the resulting matrix is also m by n matrix. And the elements here should be the pairs that added together in the same location. Right, the first element should be A11 plus AB1, and the last one in the first row should be A1n plus AB1n. And all the numbers are correspondingly changed. Right. So this is an addition. And for subtraction, it's the same thing. But the only difference is that we change the plus sign to the minus sign here. To the minus sign here. But everything else remains the same. So for example, 8974 minus 1253, so they have the same dimension, right? 2 by 2 matrix, so they can be subtracted. And the result should be, the first element here should be 8 minus 1, right? The pairs that at the corresponding location that are subtracted. The second element here, the first row and the second column here should be 9 minus 2, right? 9 minus 2 on the same location. And again, this is 7 minus 5. This is 4 minus 3, right? So the resulting matrix should be 7, 7, 2, and 1 by just calculating inside the matrix. So this matrix is the resulting, is the subtraction of the two matrices here. So we can see that for addition and subtraction, it's very easy. We just compare the elements in the same locations and to do addition and subtraction accordingly. And so the resulting matrix should have the same dimension as the original two matrices. We don't change the dimension by addition and subtraction.